Hi everyone, and welcome to our happy deep learning road trip for physicists. Today we will master the optimization of network parameters. Before we even think of training, we polish our data. We ask, is every feature ready for stable numerical work? We keep that question in mind while we move to our first concrete tool, zero centering. Here you see xi minus the mean value of xi. We simply shift every variable x, or as computer scientists say, feature x, so that its average becomes 0. That puts positive and negative numbers on equal footing. Now we divide the centered value by sigma I, the standard deviation of that same feature. Each feature now has unit variance, which keeps any single variable from dominating the learning process. For pixel intensities, spectra, or anything that already has hard bounds, we can use min-max normalization. It rescales xi so that it always lives between -1 and +1. For this, we subtract the minimum, divide by the full range, stretch by 2, and finally shift down by 1. When a feature spans many orders of magnitude, we tame it with the logarithm, as shown in the first line. Or if small values matter most, we use the exponential decay in the second line. Both tricks spread information more evenly across the number line. What is an epoch? One epoch is one full pass through all training examples. Easy to count, perfect for progress bars. We rarely process the whole dataset at once. Instead, we grab a mini batch, say 32 samples, improve the network parameters, thus take a tiny step. Small batches add noise, big batches cost time, so choose wisely. To train a network, its parameters must start unequal, or every node would learn the same thing. So we draw random numbers for the weights W and keep biases B at 0 for now. In Xavier or Gloerot initialization, spreading weights is done by Gaussian sigma squared equals 2 divided by n in plus n out. That choice preserves the variance of activations for hyperbolic tangent layers. In the He initialization for ReLU layers, we drop n out from the denominator because the rectified linear unit kills half the values. On screen, you now see two friendly network cartoons. In order to adjust the parameters of such a network so that we achieve our physics model, we aim for a single scalar that tells us how well the network is performing. This scalar will be the result of the objective function, also referred to as cost or loss. The lower the scalar, the better, and 0 is perfect, though perfection rarely happens. On the left, one input node feeds a single output node. This can be used for a regression challenge with a continuous output value. This is a perfect playground for the so-called mean squared error, which we will discuss next. On the right, 3 input nodes fan into 2 output nodes. This network can be used for classification purposes. This setup we will later use for explaining so-called cross-entropy. We assume that our training data have a true value y to be reached as closely as possible by the network prediction z. We refer to this true value as label and compare every prediction z with this true label. Training a network with that guiding label is referred to as supervised training. Now we make the objective function L-concrete for regression challenges. The first line says mean squared error MSE, which is the mean of the squared difference between the network prediction z and target label y. The second line turned that idea into practice. As the objective function L, we average the squared difference over k samples. Everything is positive. Everything is differentiable, which will later be important when adjusting the network parameters. Training a classification network is a bit more involved. Let us first make a short stop in statistical mechanics and information theory. This line defined entropy in Boltzmann flavor. If a system has n equally possible configuration states, the probability P is 1 over n, and entropy S is minus the Boltzmann constant times log P. For the general case with unequal probabilities of the states, we need to average log Pj. This leads in the second line to the sum of the product Pj times log Pj. Speaking in terms of information theory, entropy measures ignorance. Higher entropy means less knowledge. From entropy, we leap to cross-entropy, our workhorse to train networks for classification challenges. With the first sum, we calculate the average across k event samples. With the second sum, we take into account all classification categories, a total of m classes. Here, Qj stands for the class probability predicted by the network. The actual true class probability is indicated by Pj. Let us restrict here to two classes m equals 2, one is signal, one is background. Using only two classes permits us to write the sum explicitly with the signal probabilities P1 and Q1. The backgrounds are 1 minus P1 and 1 minus Q1 respectively. To understand how cross-entropy is used as an objective function that is minimized during network training, let us compare some numbers. We take an example of a signal event that is P1 equals 1. The network may be rather wrong predicting Q1 equals 0.2. Then the objective function returns 0.7. If network prediction matches better with Q1 equals 0.8, the objective function shrinks towards 0. Thus, training classification networks is done by minimizing the cross-entropy objective function. And that is it. We pre-processed inputs, sliced data into batches, initialized weights smartly, and optimized with losses tailor-made for regression or classification. Armed with these tools, your neural network will train faster and converge better. Thanks for watching.